Previously in Chapter 19, we've discussed magnets and magnetic fields, as well as magnetism from electricity. Now we're moving on to the final section, which covers magnetic force. Below I've written the equation for force on charges moving through magnetic fields. It states that F equals QVB, or the magnetic force equals the charge times the velocity of the charge times the strength of the overall field. The units for magnetic force are the Tesla, which is written as a capital T. When we're calculating magnetic force, a different right-hand rule applies. This time, hold your hand open with your palm facing forward. You want to line up the direction of your fingers with B, which is the direction of the magnetic field, and your thumb with V, the velocity of the charge, which will always be perpendicular to the magnetic field. If you line up your hand in this way, the palm of your hand will point in the direction of the magnetic force, which is essentially an arrow pointing straight through your palm. For current-carrying conductors, we have a slightly different expression for magnetic force. This states that the force is equal to the magnetic field, or B, times the current, I, times the length, L, of the conductor. Let's take a look at how this works in some practice problems. Number 1. A proton, which we know has a charge of 1.6 times 10 to the negative 19th coulombs, moves perpendicularly to a magnetic field of magnitude 4.2 times 10 to the negative 2 teslas. What is the speed of the particle if the magnitude of the magnetic force on it is 2.4 times 10 to the negative 14th newtons? So we have our equation F equals QVB. And we're trying to solve for the speed of the particle, so essentially the magnitude of V. So we know that the force on the particle is 2.4 times 10 to the negative 14th. We also know Q, the charge, because this is a proton, so it's 1.6 times 10 to the negative 19th. We're solving for V, and then for B, we have 4.2 times 10 to the negative 2. So now we're ready to simplify by dividing this side by 1.6 times 10 to the negative 19th times 4.2 times 10 to the negative 2. This allows us to isolate V, which, if we simplify, we find to be 3.57 times 10 to the 6th meters per second. Number 2. If an electron, which has a charge of negative 1.6 times 10 to the negative 19th coulombs, in an electron beam, experiences a force of 2 times 10 to the negative 14th newtons, while traveling at 1.5 times 10 to the 6th meters per second, what is the magnitude of the magnetic field? So here we can use our rearranged equation where we're isolating B, the magnitude of the field, and then that equals F divided by Q times V. Now we're ready to plug in the variables. We're solving for B. That's equal to the force, which is 2 times 10 to the negative 14th newtons, divided by negative 1.6 times 10 to the negative 19th, times 1.5 times 10 to the 6th. Now we're just solving for magnitude, not direction, so we can disregard this negative sign. And if we simplify, we're left with B equals 8.3 times 10 to the negative 2 teslas. Finally, number 3. A 6-meter wire carries a current of 7 amps. A magnetic force of 6 times 10 to the negative 6 newtons acts on the wire in a perpendicular direction. Find the magnitude of the magnetic field producing the force. So this time we're using our equation for magnetic force on a conductor, where we have F equals B, or the magnetic field, times I, the current, times L, which is the length of the conductor. We know the force is 7 times 10 to the negative 6th. We're solving for B, and then we have the current, which is 7 amps, and the length, which is 6 meters. We'll divide both sides by 42, isolating B, to get that B equals 1.7 times 10 to the negative 7th teslas. So this has been Chapter 19, the last chapter I'm covering in Holt Physics, which is used for AS Physics at Menlo Atherton High School, and will hopefully come in handy even if you don't go to MA. I'm Annika, and thanks again for watching these videos.